and yet, you know, I've always found it a bit silly to read what all of you can read faster than I can speak. So yesterday I learned from Fred a very nice way of introducing the speaker, so she'll speak to you about her wonderful things.
Thank you, Andre. Thank you all for coming. I'd like to thank the organizers for this invitation. Is this mic level okay? Yeah. Okay. All right. I'm going to tell you about a project today that I'm working on with Danny Caligari and Alden Walker. It's a project that we're about to wrap up, but there's still many questions that we'd like to answer and some kind of neat things that we don't completely understand yet. This is a project in dynamics and geometry. But before I tell you about the particulars of that project, I'm going to start with a discussion of what happens for the quadratic family of polynomials, z maps to z squared plus c, in the realm of complex dynamics. And then I'll tell you specifically about we're doing, which has some sort of surprising applications to polynomials, algebra, and is in fact related sort of mysteriously to other dynamical systems and dynamical quantities that have been recently studied. Okay, so we'll start with a preliminary discussion of the quadratic family, z maps to z squared plus c. P sub c here is this particular quadratic polynomial mapping the complex plane to itself. Whenever you have a polynomial, you can define a non-empty compact invariant set, a subset of the complex plane called the Phil-Julia set, which by definition consists of all points that do not escape off to infinity under iteration. So the sequence of iterates is bounded. So here are some pictures of what those sets might look like for the quadratic family. The parameter c here, this is a complex number. When c equals 0, the Phil-Julia set is just the closed unit disk. When c equals -1, you get this nice fractal here. This is known in some circles as the basilica fractal. When c equals I, you'll get this guy here. This is the dendrite. The Phil-Julia set has empty interior. And when c equals -2.5, you get this set here. This is a Cantor set. So this shows you just some of the behavior that you can get as you vary the parameter c and study the dynamical set in the complex plane. I want to point out that every single one of these green pictures has a distinguished point. There's a distinguished point in the dynamical plane for each one of these guys, the center of symmetry. This is a critical point, the unique critical point for the quadratic polynomial, and it's geometrically distinguished. It's the center of symmetry of the Phil-Julia set, and in fact, it's dynamically distinguished also. We'll talk about that in a second. Okay, so for the quadratic family, there's a fundamental dichotomy. Either the Phil-Julia set is connected, or it is a Cantor set and totally disconnected. Okay. So there are perhaps three subsets of parameter space that might be of interest to us. So remember, C here is our complex parameter. Our parameter space is a copy of the complex plane, and we might want to study three particular subsets just to see what we can say about how the shapes of these Phil-Julia sets vary as you move the parameter. So the first set I'll call script M. By definition, this will be the set of all parameters C for which the Phil-Julia set is connected. The set script M prime will be the set of all parameters C for which 0, the critical point or the center of symmetry of these sets, is inside the Phil-Julia set. And then the set M double prime, which consists of all parameters C for which the dynamical set is both connected and full. So in this talk, I'll use the word full to mean a subset of the complex plane whose complement is connected. Okay, so a set that's full has no holes in it. All right, so you might want to study each one of these sets in turn, and in fact, it turns out that they coincide for this particular family. So the set drawn in black here is the Mandelbrot set. This is parameter space, our C parameter plane for z maps to z squared plus c. The set M, as I said, is the Mandelbrot set, and by definition, it consists of all parameters C for which the Phil-Julia set is connected. It is the connectedness locus for this family. The set M is in fact equal to the set M prime. This result is just a standard complex dynamics result. It goes all the way back to times of phi2 that the Phil-Julia set is connected if and only if it contains the critical point or the center of symmetry. So those two sets coincide, and in fact, the reason that these sets are called filled-Julia sets is because they are in fact always full. So if it's connected, it will be full. So the set M double prime coincides with the set M also. So that's a maximum modulus argument to tell you that these things are all full. They have no holes in them. So all three of these sets are the same, and they're equal to this set here. So we can ask about certain features of the Mandelbrot set. This has been very well studied. It's sort of a central object of interest, and it is, in a strong sense, universal in a way that you can make precise. Here are some facts about it. It is compact. It is connected. This is a theorem of Doherty and Hubbard, and in fact, it follows from their arguments that the Mandelbrot set is also full as a subset of the complex plane. So the Mandelbrot set doesn't have any holes in it either. Okay. It is equal to the closure of its interior. Now, we don't yet know what all of the interior of the Mandelbrot set looks like, but we do in fact know that if you take the topological closure of the set of interior points, you'll get the Mandelbrot set back. And it is unknown whether or not this set is locally connected. Jeremy gave us an update on this problem last night. This is something he's working on. Okay, I do want to make a couple remarks. Among the components of the interior are the so-called hyperbolic components. These are components of the interior where the critical point is attracted to an attracting cycle. And as you move through this component in parameter space, the dynamics changes very predictably. So as you move across one hyperbolic component, you'll always have an attracting cycle of a certain period, and the Julia sets will in some sense have the same shape. They will move continuously. And this picture is extremely well organized with respect to those hyperbolic components. So here's the big central component here. This is a hyperbolic component that contains the parameter 0. Here's a hyperbolic component, the interior of this component, which contains the parameter -1, and so on. Every hyperbolic component has a unique center where the critical point is periodic. And in fact, you can extract some finite combinatorial data to label these hyperbolic components in parameter space and build a roadmap that helps you navigate your way through this set. Okay? And then you can really understand much of the combinatorial structure of this set with the hyperbolic components. Now, as I said, we don't know that every component of the interior is hyperbolic. That's closely related to this question here. Okay, but the point is those components are nice, and you can use finite data to tell them apart and to navigate your way through this set. And just one remark about how the Julia sets move as you move in parameter space. As soon as you cross the boundary of the Mandelbrot set, the Julia sets will move discontinuously in the Hausdorff metric. Okay, so that's it for our quadratic polynomial warm-up. Let's keep this in mind, and now I'll tell you about the particular family that Danny Alden and I are studying. So we're studying a little bit more of a generalized dynamical system. We're studying iterated function systems. So most generally, if an iterated function system is the following object, X is a complete metric space, and we'll take a finite set of contractions mapping X to itself. And it's not so hard to see by using essentially the same argument that proves the contraction mapping fixed point theorem that there's a non-empty compact attractor in the dynamical plane that you can get by taking just a generic point and mapping it forward under different maps in your generating sets. The accumulation set of the forward orbit of that point will be this attractor. Okay, that's called lambda, and it has the property that it's equal to the union of its images under the generators. So in fact, lambda looks like it has a bunch of small copies of it inside itself, because all these maps are contractions. So here's an example. You can get the Sierpinski gasket as a limit set for an iterated function system with 3 generators. So what are the generators? Well, you just look at the affine map of the plane that takes this triangle to this triangle. That's one generator. The map that takes the big triangle to the top triangle, and the map that takes the big triangle to this triangle over here. There are your 3 generators, and this will be the limit set for that iterated function system. Okay, so these things are made up of small copies of themselves at smaller scales. Okay. So I'll be studying a particular parameterized family of iterated function systems. The family I'll be looking at will have 2 generators in it. They'll be acting on the complex plane. C here is a parameter. These maps are supposed to be contractions. They're just affine transformations or similarities. And so the scaling factor should have modulus less than 1. Okay, it's to be an IFS. And each one of these maps has a fixed point with respect to which it's contracting. These are just affine similarities, transformations of the complex plane. I'd like to say that if you study another parameterized family where the parameter is the scaling factor and that family consists of is generated by just two elements, like this one, then in fact it's conjugate to one of this form. So it might look like I'm studying some very special family, but that's not the case. Okay? And the limit set here will be the closure of the set of fixed points of the elements in the semigroup generated by these two generators. All right. So if you wanted to draw this limit set, what might you do? So the limit set is a compact subset of C, so you could take a large disk, which will contain it, and then you can map it forward under words of a given length, words in the generators. So for instance, I could take the disk and map it forward under words of length 1. That, of course, is just mapping it forward under each of the generators. And so my one disk will become two disks. I can look at those two disks and then map those two disks forward under F and under G. And then I'll have 4 disks, and then 8 disks, and so on. So I keep mapping this one big disk forward lots and lots of times. And I can look at, this will be a nested set, and I can take the intersection over looking at words of any length. So looking at words of all the lengths and taking the nested intersection, it will limit down to the limit set. So I keep approximating it with these disks. Now, here's a picture of what I mean. So we start with a big disk. We look at it under F and under G. The blue disk is the image of the original disk under F. The orange disk is the image of the original disk under G. We get this picture. The limit set is contained in these disks. The fixed point of one of the generators is here. The fixed point of the other is here. We'll map it forward again. There are 4 disks. The limit set is going to be contained in this union of 4 disks. We'll map that forward under F and under G again. And now we have 8, and then we have 16, and so on. And so at the end of the day, we can approximate our limit set with this recipe. Okay? So throughout this talk, I'll be drawing my limit set in 2 colors. One will be blue and one will be orange. So the blue is the image of the whole limit set under F, and the orange is the image of the whole limit set under G. So you can see that the limit set here, you have a small blue copy coming from F, a small orange copy coming from G, and in fact, if you zoom in further, each of these small copies is made up of 2 small copies of the limit set, and so on. So a word in F and G will just give you a shrunken limit set, and what that word is gives you the address of where that shrunken limit set actually is in the big one. All right. So if you want to certify with a computer, I have a computer picture, and I'd like to know something topological about the limit set. So if you want to certify that this limit set is disconnected, that actually isn't too bad. So the limit set will be disconnected if at some point in this approximation procedure with these disks, the blue piece and the orange piece are disjoint. That will separate the limit set. Okay? And a computer can test that. Certifying that it's connected is much harder. We'll talk about that next. All right, so what do we know about the topology? So connectedness. The limit set is in fact connected if the blue piece and the orange piece, the image under F and the image under G, have non-empty intersection. Okay, that's an if and only if. And if the limit set is disconnected, this is related to my previous comment, then there is a topological disk which contains it so that just one image under F and one image under G are enough to separate it. Okay, so before we were taking some large enough disk and mapping it forward enough times to eventually separate the blue and the orange. This statement is saying that there is in fact one topological disk. So if you look at the image under F and G, that will be enough to separate it. And just like with the family of quadratic polynomials, there's a fundamental dichotomy. The limit set is either connected or it's a Cantor set. Okay, so here are some pictures of what it might look like. This is supposed to look like a Cantor set, but the points are very close together, so it looks a little chunkier than it should. Here, it's connected, connected, connected. So just as before, for quadratic polynomials, we can study some subsets of parameter space. But remember, my parameter space is now my scaling factor space. It's no longer a copy of the complex plane. It's a copy of the punctured disk. So I can start to write down some distinguished subsets of parameter space. To that end, I'd like to point out that just as with quadratic polynomials, there is a center of symmetry for these pictures, just like before. So remember, we're generating this limit set by looking at a two-generator iterated function system. Each function is an affine transformation and has a fixed point. The midpoint between the fixed point of F and the fixed point of G will be a center of symmetry for the limit set. And you can see it in these pictures. So here it is here. It's right there for this one. So this is playing a role of a type of critical point. Okay? So just as before, in the quadratic family of polynomials, we could write down the definition of 3 subsets of parameter space and ask, well, are they all the same? Are they all different? What do they look like? And then study those particular subsets. So there's our family up at the top. The set M is the set of all parameters for which the limit set is connected, the connectedness locus again. The set M prime is the set of all parameters for which the limit set contains the critical point, or the center of symmetry. And the set M double prime is the set of all parameters for which the limit set is connected and full. So remember, the limit set is full if its complement is connected. Okay. So what actually happens? Well, each one of these sets is a closed subset of the punctured disk. And in fact, no 2 of them are equal, but you have this containment relation. So we can see that here. Let's just go through some of these examples. For this particular parameter, the limit set is disconnected, so it's not in any of these sets. So it's disconnected. The center of symmetry is not inside the limit set, and it's disconnected. So of course, the corresponding parameter is not in the set M double prime. For this limit set here, it is connected. The blue and the orange intersect, but the center of symmetry is not inside the limit set. So this picture corresponds to a parameter which is an M, but not M prime. And also, this parameter is not an M double prime either. You can see that it's not full. Over here, we have a limit set that is connected. The center of symmetry is inside, but this thing isn't full either. So this parameter is inside the set M and inside the set M prime, but not in the set M double prime. And over here, you have a limit set where the blue and the orange intersect in exactly 1 point. In fact, the center of symmetry necessarily. So the corresponding parameter is in fact in all 3 of these sets. So you can use some relatively simple arguments to prove this containment relation. Okay? All right. So what do these sets look like? Now we know that they're all different. Oh, I should make a remark about continuity. So in contrast to the family of quadratic polynomials, as you vary the parameter for this particular iterated function system, the limit sets move continuously in the Hausdorff metric. That's very different from what happens for z squared plus c. Okay, so here are 2 pictures. These were drawn with this great computer program, which is available at this URL if you'd like to explore and look at it. In fact, I'll show it to you in a second. So on the left here is a picture of the connectedness locus, the set of all parameters in our parameter space for which the limit set is connected. On the right is that set M prime, the set of parameters for which the limit set contains the center of symmetry. And based on what I said before, the set on the right is a subset, a proper subset of the set on the left. Sorry, the colored set. Good question. Yes, the colored set is the set that you're looking at, yes. Good question. So Sturgios asked me about the coloring. So these sets are colored according to how hard the computer had to work to do something. And I'll make more comments about that in a second. So just a couple of remarks about the geometry of these sets. So you'll notice one thing, there are prominent spikes or whiskers that are piercing this large Great Lake in the center here. So those actually really are there. There's an open subset. This point here is 1/2. This point here is -1/2. There's an open subset of the complex plane containing 1/2 that intersects the set M. Oh, my pointer's dying. The set M in just a subset of the real numbers. Similarly over here. So those spikes have no complex decorations on them. Thanks, Yair. Those spikes have no complex decorations on them. That's where the set is just a subset of R. Okay. Moreover, there's some symmetry. So each one of these sets is symmetric with respect to reflection across the real axis and with respect to reflection across the imaginary axis. So in fact, if you want to study these sets, it suffices to just focus your attention on 1/4 of the picture. You don't have to study the entire thing. Okay, so let me do some computer experiments now, just to show you some, thank you. Oh, I should have set this up earlier here. Okay. Oops. Okay. All right, so this is this wonderful program that we've been using to explore this iterated function system. It was mostly written by Alden Walker, who's this great guy at Chicago. On the left here is the dynamical plane. On the right here is parameter space. This is some approximation to the set M. So as I drag my cursor around, hopefully you can see, let's see here. Hopefully you can see how the limit set changes on the left in the dynamical plane. So as I'm walking through the white region, you can see that the set is a Cantor set, and then as I cross over into the colorful regions, it connects up. The boundary looks kind of interesting. Down here where those spikes were, I can refine this picture a bit. Down here where those spikes were on the real axis, the limit set becomes an interval. Here's the point 1/2, where the blue and the orange touch in just one point. And then if I move a little to the left, it separates completely, and I get a Cantor set back. So we can start to zoom into this picture. Let me see here. Zoom into a point on the boundary. And then I'm refining how the computer is drawing the connectedness locus. So you can move around here. Okay. And let me see here. Okay, there we go. That looks like something. Aha, there it is. So I'm here, and I'll zoom in a little more. So there's the boundary. It looks pretty nice and fractal. And one thing that we were very surprised to find was this. Let's zoom in a little more. Okay, so what is that? All right. So, in fact, the computer has found a hole inside the set M. It's found a component of the complement of the connectedness locus that isn't that large Great Lake in the center. There's the central component. We were moving around the parameter before, looking at the Cantor set change, and now we've found a hole inside M. We found what I'll call an exotic component of the complement. And in fact, if this thing is really there probably are infinitely many of them. In dynamics, of course, you don't usually ever find one of something. So if you zoom in various areas with this program, it's actually really neat. You can see these things. They're arranged in families, which suggests some kind of renormalization phenomenon, and you can try to study them. And that's what our project is about. Okay, back to Keynote. All right. So here's another zoom into M and into the connectedness locus. The set M prime we could also study, but I'll focus my attention on M for the time being. So here are some of those holes. I think this was the one that I just showed you. Here are some baby ones, some smaller ones spiraling around it. Here's a nice family. This is the central Great Lake component. Here's a nice family of holes spiraling down to some limit. Okay, so what are these holes and why are they there? Are they there? Okay, so we are certainly not the first people to have studied this particular family or this connectedness locus, this subset of parameter space. As far as we can tell, this goes back to 1985 with Barnsley and Harrington, who proved, this is the original picture, who proved that this set M really does have those real whiskers, so that there are no complex decorations in a neighborhood of 1/2. Okay. In 1988 and 1993, Thierry Bouch wrote some papers where he proved that the set M and, in fact, the set M prime are both connected and locally connected, which is kind of interesting if you compare this to the Mandelbrot set discussion. In 2002, Christoph Bandt actually found that the set M is not full as a subset of the open unit disk. So he was the first one to discover that these holes actually existed. He proved that there is at least one exotic component of the complement. There's his original picture. And he wondered about the interior of this set and conjectured that the interior of this set is in fact dense away from the real axis. We already know that the real axis is going to be a problem because the set is very thin there. There are those whiskers. There's no way that the interior is dense in the whole thing, but if you remove the real whiskers, maybe you can say something. And a lot of people, this list is certainly not exhaustive, but Slomiak and Ju and Slomiak and some other people have studied this from a topological point also. They proved that M has dense interior in a neighborhood of the imaginary axis. Okay, so this is just a small subset of the literature that exists about this particular family. And what I'm going to focus on is the set of interior points. So there are two results I'd like to share with you. The first is that the interior of the connectedness locus is in fact dense away from the real axis. So staying away from those real whiskers where you know that you have no interior points, the interior is dense. And the second theorem is that there are in fact infinitely many holes in M. There are infinitely many exotic components of the complement of this thing. Figuring out what they mean and how they're arranged is a really interesting question, and we don't understand that yet. Okay. All right, so let me just set us up with a result of Thierry Bouche. So he knew something about the interior. So back in 1998, Thierry Bouche proved that the set M, in fact, contains this annulus. So this number is like 0.7, which is right around here-ish. So there's a solid annulus here where there aren't any holes, and you have lots of interior, so sort of toward the edge where the picture gets darker. The holes actually seem to exist closer to the boundary outside of this region here. Okay, so we have this sort of annular region around the outside where we know there are interior points. So remember that for later. Okay, so the way that this argument goes involves a discussion of what I'll call transverse intersection in a way that I'll sort of make up a new definition. So I want to think of a compact path-connected subset of the plane. And I want to say that this set intersects another set. In fact, I'm going to be applying this notion to a set intersecting a translate of itself eventually. That's why these two things look the same. But I'll say that this set, the red set and the purple set, intersect transversely if the following hold. The union of these two sets is path connected. And the boundary has the following property. So the boundary here is connected, and the boundary has points that alternate from boundary of the red region to boundary of the purple to boundary of the red to boundary of the purple. And maybe there are it alternates in other ways later, but I really only need those first four alternations between red points, purple points, red points, purple points. And here's why. I'd like to have this because what I'd like to do is pick a red point from up here and a red point down here and draw a path that's completely contained in the red set. Pick a purple point from here and a purple point from here and draw a path that's completely contained in the purple set. Okay, and I want to say these sets intersect transversely if they have this property, if I can do that. So these paths are linking up, and I want to use that to prove something a little bit later. Okay, is that clear what I mean? All right. And one thing that's kind of interesting is you can ask, well, what shapes of subsets of the complex plane have this transverse intersection property? So in fact, if you have a set that's not convex, and this will be key for the discussion in a few minutes, if you have a subset of the plane that's not convex, then there's a direction that you can shift, that you can translate that set off of itself so that the original set, which is red in this picture, and the image under the shift, which is purple in this picture, have this transverse intersection property. So that's why I drew two copies of the same set there. If the set is convex, you won't be able to do that. Okay, I can't shift this around to have that alternating intersection property. Okay, so there's something about this transverse intersection and convexity that's going to become important for us in a few moments. Okay, so how are we going to use the computer to rigorously prove that these holes exist? So I mentioned before to you that in order to prove with the computer that a limit set is disconnected, you can do rigorously. You just have to find some depth where the blue approximation and the orange approximation are disjoint, and that certifies it rigorously that at that parameter the set is disconnected. To prove that it's connected is harder. So this is how I'm going to prove that given a parameter, given the limit set at the parameter, the limit set is connected. I'm going to use a method which involves something that we call traps and that idea of transverse intersection. Okay, that requires a little lemma. So we'll take our parameter c, and we'll draw f of lambda c and g of lambda c, the blue and the orange piece of the limit set, and suppose that their distance is less than or equal to some positive number delta. Okay, so what I'm going to prove to you is if you have one of these things called a trap, then in fact the limit set has to be connected because the distance between the blue and the orange actually is 0, meaning that these two things will intersect, so the limit set will be connected. Okay? So let's suppose that the distance is less than or equal to some positive number delta. And what I'd like to do is explain why the existence of something I call a trap will prove that the limit set will be connected. Okay, so this requires this lemma. The distance between the blue and the orange is less than or equal to delta. Then the delta over 2 neighborhood of the limit set is in fact path connected. It's just a nice topology exercise using the IFS. It's an immediate corollary that if u is a word of length n, so when I give you a word of length n, what I'd like you to think about is a small copy of the limit set. It's been scaled by a factor of c to the n, and what the letters in the word u tell you are where in the limit set it lives. It's the address. Okay, but it's just a small copy of the limit set. Okay, so if you know that the large neighborhood, the neighborhood of the large neighborhood, the delta over 2 neighborhood of the large limit set is path connected, then it follows by induction that a neighborhood of that size, a scaled down neighborhood, c to the n times delta over 2 of this small copy of the limit set is also path connected. All right, so what's a trap? So a trap is a pair of words of length n. The first word, u, ends with f. The second word, v, ends with g. That condition is just saying that u, the small copy of the limit set you get from that word, is blue. V, the small copy of the limit set you get from that word, is orange. Okay? A trap is a pair of words of this form so that this neighborhood of this small blue copy and this neighborhood of this small orange copy have this transverse intersection property that I was telling you about before. So this is the picture to have in mind. Here is the small blue copy, which turned green. Here is a small orange copy, which turned yellow. And these two things intersect transversely. To say that you have a trap means that you have a small copy coming from the word u, a small copy of the limit set coming from the word v, that intersect transversely. And now I'm going to conclude that if they intersect transversely, the orange and the blue, then in fact they have to intersect, which means that the limit set has to be connected. Okay, so the distance, the infimum distance, the distance between the blue copy and the orange copy is less than or equal to the distance between the small blue copy and the small orange copy. This follows immediately from the definition of how we're measuring distances, because this is a subset of this is a subset of this. And then the distance between this small copy, this small blue copy, and this small orange copy is less than or equal to this quantity here. And that comes from this condition that these two neighborhoods intersect transversely. But this means then that the distance between the large blue piece and the large orange piece has to in fact be 0, because c is less than 1 in modulus. All right, so that implies that the limit set is in fact connected. So it implies that our parameter is inside the connectedness locus, but in fact, this traps idea, this intersection idea, persists under wiggling. So you can wiggle around, the limit set moves continuously, and you'll still have this transverse intersection property. So this gives us an interior point of the connectedness locus. Okay, so to certify that we have a parameter which is in the interior of the set M, what we do is we tell the computer to look for traps. It's going to look for words U, and V, look for small copies of the limit set that have this property. Okay, so finding traps, what do? So we'll take a parameter and draw the limit set, draw some approximation of it, using the algorithm I outlined for you at the beginning. You take a large disk and map it forward lots of times. You get an approximation of it. If that limit set is not convex, then you can find what I'll call good directions or trap-like balls. There are directions where you can shift the limit set off of itself so that the original set and its image under that shift have this transverse intersection property. So I take some approximation on the computer to my limit set, and I look for good directions that I can shift this thing. And I ask the computer to remember those good directions. Okay, so what the computer will do is it will find these good directions and put them in little balls here. They're little open sets. Okay, and it remembers what they are. Okay, so then what it does is it searches through all words U and V of a given depth, and it looks at this displacement vector to figure out if this displacement vector is actually parallel to one of these good directions. If it finds it, then it knows, then that actually will give you a trap, that will give you a good direction, that will give you a small copy. It will tell you how to zoom into the limit set so that a little orange copy and a little blue copy intersect that way. And the displacement vector between the centers of symmetry will be parallel to that good direction. Is that clear? It's hard to explain. So that's what the computer is doing. It's searching for words of a given length that give you small copies of the limit set that have been translated off of each other in these good directions to give you this transverse intersection property, thereby establishing that the set is connected, and in fact that the parameter was in the interior of the connectedness locus. So here, this is what the computer does. This is actually how it's coloring that picture. It colors the picture M according to how hard it is for it to find traps at a given depth. So this is a picture, a subset of the connectedness locus. All these blobs here show you regions of the interior where there are traps, okay, of length 20. This shows you where there are regions of the interior of traps of length 35. You cover much more of the set. So that's how we're able to certify that we have interior points of this set. That's how we're able to get our hands on that. So in order to prove that there is an exotic component, that the set M has holes in it, all we have to do is draw a loop with the computer inside the connectedness locus and make sure that we can cover it with these traps, these balls of traps. Okay, because the computer certifies you have these large balls, you can cover this path with those balls, then it in fact is a subset of the interior. So that will give us that the loop is in the connectedness locus, and then we have to just prove that there's a parameter on the inside where the limit set is disconnected, but as I mentioned before, that's easy. Okay, and that gives you a proof that these holes exist using the computer. All right, so in fact, the argument can be promoted. We have a special case where we can get infinitely many holes using a limiting spiraling argument, which I won't tell you about today. So we can get infinitely many of them also, again, using the computer. To get that the interior is dense and to establish this conjecture of Christoph Bandt, there was this convexity issue that I mentioned. So if the limit set is not convex, so what we're going to do is take a parameter that we know is inside the connectedness locus, and I'd like to give you an argument about why you can approximate that parameter with interior points, with parameters in the interior of M. So you take this parameter where your limit set is connected. If the limit set is not convex, then you can find these good directions, these trap-like vectors, where you can shift this thing off of itself. Okay? So because the original parameter that you started with was in the connectedness locus, the intersection of the blue and the orange is non-empty, so there are words U and V, a small copy of the limit set which is blue, a small copy of the limit set which is orange, so the distance between their centers of symmetry is very small, and you wiggle the parameter c around to make this vector be trap-like. So you can find a sequence of traps which approximates the parameter, the connectedness parameter that you started with. Okay, so this is just a rough idea about how to approximate, if your limit set is not convex, how to approximate the parameter and parameter space in the connectedness locus with a sequence of interior points in the connectedness locus. Okay. What if the limit set is convex? Well, this is a result that goes back to one of Slomiak's papers. He figured out exactly where the limit set is convex. The limit set is convex if and only if the parameter is of this form, in which case the limit set is some kind of polygon. And that's drawn for you here. Here's our set M. These red spikes show you all of these angles here, all of these complex numbers. So these red spikes are precisely where the limit set is convex. So this is where my argument from the previous slide about taking a parameter where the limit set is not convex and approximating that parameter with interior points in the connectedness locus will fail. Note here the real whiskers are part of this locus, as I said before. Okay, the limit set for these real whiskers, it's a line segment. It's convex. All right, but we can establish the theorem that says that the interior of this set is dense away from the real axis because the only region that we have to worry about are the real whiskers here. So we know from Thierry-Boucher's results, because there's this closed annulus that's contained in this set, that the interior is dense inside here. So outside of this yellow circle was that Thierry-Boucher region where the closed annulus is completely contained in the set M. So the interior is dense there anyway. So the points that remain are the points on the other side of the yellow circle, but all of the limit sets are convex there, so the argument from the previous slide will work everywhere except here, where we knew there was a problem anyway. Okay, so this establishes Band's conjecture that the interior is dense in this set away from the real axis. It's kind of neat that it sort of boils down to this question of where the limit set is convex. Okay, so as I said before, it would be really great to understand why these components are there and to classify them. So taking our inspiration from what happens with z squared plus c, you've got the Mandelbrot set, you've got all of the hyperbolic components of the Mandelbrot set, and I mentioned that you can use finite combinatorial data to label the hyperbolic components of the Mandelbrot set to build yourself a roadmap to tell you how that set is organized, how it's structured, to tell you a lot of information about it. It would be great if we had some kind of combinatorial invariant or something, some piece of data that distinguished this teeny tiny hole in the set M from this one, that distinguished this hole from the Great Lake in the middle, this hole from this smaller one, this hole from this one. So we don't have that mechanism in place yet, but when you look in the dynamical plane, it's clear that there is something to say. Furthermore, from the z squared plus c case, those hyperbolic components, that data that I mentioned, is dynamical data. Those components are dynamically distinguished. Remember what we're looking at here. It's a little backwards. I'm trying to tell components in the disconnectedness locus apart. These are components in the Cantor set locus. Topologically, all Cantor sets look the same. So there has to be something else. It's not a topological reason why these components are there. There in fact isn't even a dynamical reason, because it turns out that the action of the iterated function system on the limit set, if the limit set is a Cantor set, they're all conjugate. So there should be some other reason, and I'll say that it's a geometric reason when I show you the following slides. So there should be a geometric reason for these different components. So here, this is this parameter up here. If we click here with the computer, we'll get a Cantor set. So again, this is a chunky Cantor set. It should look more like a dust of points, but it doesn't. But there does seem to be some kind of combinatorial or geometric information about how these two pieces fit together, the orange and the blue. So you can zoom in here and you'll see this interlocking gears picture like this. So if there's a way to quantify, it sort of looks like a zipper. If there's a way to quantify exactly what's going on, maybe that data can be used to distinguish this hole from the other ones. If I use the computer and I clicked here, in this teeny tiny hole right there, this picture would change ever so slightly, and the combinatorics about how these teeth are locked together would change. It would shift. Okay, so there is something that's distinguishing these holes apart, and it appears to be this whatever geometric phenomenon is causing this locking. So here's a movie. I'm going to walk around the boundary of this hole here and watch this picture. Look at how the geometry of how these things are, the blue and the orange are locked together, changes. As you walk around. Okay, so you can see as you approach different points on the boundary here, this combinatorics changes. It would be great to have an understanding of that. So that's something, I think that's a really neat problem. Okay, I do want to relate this to some other sets that have shown up. There's a neat connection with this whole discussion to polynomials and power series. So let me just remind you what our maps are. So we have the map F, the map G. All right, so if we take a word of length n in F and G, so that's called W here, and we just sort of look at this as composing two affine transformations of the plane. So I'm going to get some larger affine transformation that takes z to this. So it's going to, the scaling factor is going to be c to the n. C is my parameter, and then this is the constant term here. Now, you can see that these coefficients are going to be determined by which letter, either F or G, you picked. And in fact, these coefficients are either going to be +1 or -1 coming from this +1 and this -1 here. So when you compose these two functions together, you look at a word of length n, you'll get some affine transformation of this form back, where the coefficients ai are +1 or -1 depending on what letter you picked at stage I in the word. So for instance, the constant term a0 over there is going to be 1 if your word ended with an F, and -1 if it ended with a G. So it will be 1 if your word gave you an address of a blue point in the picture. It'll be -1 if your word gave you an address with an orange point in the picture. So in fact, using this description, remember the limit set, so for a given value of c, you have your dynamical picture here. The limit set you can get by taking some generic point, some point in the plane, like z here, and just mapping it forward under words in F and G and looking at the accumulation set of the orbit. So with this description here, you can see that, in fact, the limit set is going to coincide with values at the parameter c of power series with coefficients in +or -1. Okay, because you just you map this, you take your point, you map it forward under maps of this form. This term becomes negligible. The point you started doesn't actually matter. So you're getting values of power series with +or -1 coefficients at the parameter c. This is kind of a neat description because it tells us another way to think about the sets M and M prime. So remember, the set M is the connectedness locus. It's where the blue and the orange intersect. So if I draw my limit set and the blue and the orange intersect, then obviously there's a point in common. What is the address of that point? So this point is in the limit set. Because it's in the orange piece, it has a development, it has an address where the constant term a0 is -1 because it has an address that ended with G, but it also has a development or an address where the constant term ended with +1 because it's a blue point. It's in the intersection. So you write down the two addresses for this one point. They're equal to each other. You rearrange that equation, that will give you a power series in the parameter c with -2, 0, and -2, 0, and +2 coefficients. So the parameter c turns out to be a root of such a power series with -2, +2, and 0 coefficients, which of course is just a root of a power series with -1, 1, and 0 coefficients. So you can completely characterize the connectedness locus as a subset, the subset of D star, which consists of roots of power series with ±1 and 0 coefficients. So we're really studying roots of power series, which are just closures of roots of polynomials. So here's where sort of the neat algebraic connection comes in. Similarly, that set M prime, which remember consisted of all parameters for which 0, the center of symmetry, was in the limit set, also has a description in terms of power series. So if you have a parameter for which 0 is in the limit set, that means that 0 is a root. That means that C is a root of a power series with ±1 coefficients, because you can write 0 as a series in the parameter C with ±1 coefficients. So the parameter C was a root of a power series with ±1 coefficients. Okay, and with this description, it's pretty clear that this set is a subset of this set. So thinking along these lines, now you can sort of, we had this IFS description, we had these sets, we were studying them from a topological point of view, but now there's this connection with roots of polynomials, and in fact, this intersects other areas also. Maybe you've seen this picture. If you Google the beauty of roots, you will see it. It's kind of amazing. So Sam Derbyshire just decided one day to plot all the roots of all polynomials with ±1 coefficients in the same copy of the complex plane. And he did that with Mathematica, and this is his picture. He got up through degree 24 to draw this picture. So based on what I said in the previous slide, this beautiful picture, the set that's inside the disk, so here's the unit circle in this picture, the subset of this picture that is inside the disk, if you take the topological closure of it, coincides with our set M prime, this beautiful fractal, which has a description in terms of a parameter space coming from dynamics now, and that dynamical description can be used to somewhat understand the fractal appearance of this set of roots. Okay, so this set, we're not really looking outside here. Remember, our parameter space is a subset of the disk. This set is symmetric with respect to z maps to 1 over z, of course, because if z is a root of a polynomial with ±1 coefficients, and 1 over z is also. Okay, and this is sort of my favorite connection I like very much. So this is a picture from page 1 of Bill Thurston's last paper. It's called Entropy in Dimension 1. And one thing that Thurston did in this paper is he was studying real maps, which take closed and bounded interval to itself. If you'd like, you can think about these as polynomials. And he was studying a certain class of them. This is a dynamical system. He was studying maps that were postcritically finite. So what that means is that every critical point of the map F has finite forward orbit or is eventually periodic. And he was interested in the question of what numbers arise as the entropy of this dynamical system. What numbers do you get? Well, in fact, it's easy to see in the case of degree 2. If F has degree 2 and it's postcritically finite, then there's a unique critical point, and it has finite forward orbit because the map is postcritically finite. So you can take your domain and range space and chop it up. You can mark it at all of the points which are images of the forward orbit of the unique critical point. This gives you a finite set of intervals here. Gives you a Markov partition, actually. And you can encode how these intervals map around themselves with a matrix. This matrix has non-negative integer entries. So there's a Perron-Frobenius eigenvalue. The leading eigenvalue of this Markov matrix, lambda, is actually equal to e to the entropy of F, okay, for this particular dynamical system. So Thurston, in fact, was studying these quantities. These are algebraic, and he proved that the numbers that you get that arise this way as entropies of interval maps, which are postcritically finite, are exactly the set of weak Perron numbers. This is a certain kind of algebraic integer. But this picture is a special subset of those. So he was looking just at quadratic polynomials, and he took some large sample of quadratic polynomials, which are all postcritically finite, mapping the interval to themselves. And for every single one of those quadratic polynomials that he had on his list, he computed this number. In fact, the minimal polynomial for that number, and plotted all of the Galois conjugates, all of the roots of all of the entropy polynomials coming from his sample of postcritically finite quadratic polynomials. He plotted all the roots in the same copy of the complex plane, and that's what you're looking at here. This beautiful set. So in fact, there's this miraculous connection that the Thurston sets, the part of the Thurston set inside the disk, and the roots of polynomials with plus or minus 1 coefficients, they have the same topological closure, as proved by Giulio Chiozzo. Okay, so these sets coincide, the topological closures of these sets coincide inside the disk, and in fact, they are both equal to our set M prime coming from the iterated function system. So somehow, this distinguished subset in parameter space for this IFS sort of knows about this set right here, and entropies of quadratic polynomials. It's sort of miraculous.
Thurston's picture is not symmetric by this.
It's supposed to be, so it's not symmetric because of the way that he drew it. We still actually don't know how. That picture has a lot of data and was sort of drawn very. Which picture? No, not 1 over z. He's asking, I think, about this reflection, or this one. No. The picture on the left, so as I said, what I'm saying, I'm talking about just inside the disk. I'm not talking about outside. Please note that this set gets very murky outside here. We don't actually know if it's different from this. It probably is, but I don't think very much is known about what that set is outside the disk. Okay. Okay, this picture was drawn by Bill Thurston. I think he knew about all of these connections. So here is in gray is this set of entropies. In pink is the set of roots of polynomials with plus or minus 1 coefficients. So inside the disk, the gray and the pink coincide by what I said before, Giulio's results. And blue is the set of roots of polynomials with plus or minus 1 and 0 coefficients. So from the point of view of our iterated function system, the blue set is our connectedness locus inside the disk. The pink set is the set where the limit set contains the distinguished point, and that set coincides inside the disk with this Thurston entropy set, which is kind of a miraculous connection. And other people have studied roots of polynomials from different points of view. Poonen and Odzlitsku studied zeros of polynomials with 0, 1 coefficients, and again, this sort of displays a family resemblance to the sets that we've seen so far, so it would be neat to kind of interpret the structure of this set, the topology of this set, maybe thinking of it as a distinguished subset in parameter space for a dynamical system like we did with the other ones. And thank you for your attention.